Tēnā koutou, and welcome to the SESOC Emerging Structural Engineers webinar, sharing highlights from the SESOC conference. My name is Laura Swass, and I am one of the committee members for SESOC ESE. This afternoon, you'll be hearing from 5 presenters from the conference. First, from our SESOC President, Michelle Grant, with her President's Address, followed by John Hare with the keynote address he gave on engineering modelling. Andrew Blackford will share his lightning talk on the design to construction process. Finally, we'll hear from Annie Scott and Hamish Tocker, who were recipients of the SESOC ESE Scholarship to attend the conference. So I'll now hand over to Michelle Grant. Michelle is a chartered professional engineer, director of a small structural engineering consultancy in the Wairarapa, and current president of SESOC.
Thank you, Laura, and welcome everybody. Tēnā koutou katoa, welcome everybody, and thank you for dialing in today. See if I can get this working right. Excellent, or not. Okay, so I believe tradition for the SESOC President's Address, as I was told at the conference, was to share with everybody all the work that SESOC and the Management Committee have been doing on behalf of our members over the last couple of years. I was only given 10 minutes at the conference, and to try and keep it brief here today as well. So just touching on some of the main things that we have been involved in. SESOC has submitted to MBIE, prepared a submission to MBIE and engaged around the Building for Climate Change. We have prepared a submission and submitted to Engineering New Zealand on the CPENG review process. We have met with Engineering New Zealand and representatives from MBIE policy team multiple times to discuss occupational regulation. We prepared our submission to MBIE also on their consultation document. We're starting to be involved in the seismic risk work group and the seismic risk work program, and this is something that we'll all be hearing some more about over the next few months. We provided feedback to the draft of a lot of standards and had a lot of our members donating a lot of hours for standards committees. So just to name a few: 1170.2, 3604, concrete production standard, timber standard. SESOC's run quite a few seminars and hosted multiple regional events, albeit with a little bit of dancing around the issues with COVID. And look, while all of this is important and it deserves more time to acknowledge all of the hours, all of the people who volunteer for ManCom put into making all of this happen, I wanted to spend some time reflecting on our conference theme. And the theme of the conference was a new beginning. And when I think about beginnings and new beginnings, I think it helps to reflect on where we are now. So where are we now? It's probably not a surprise that, in my opinion, now our profession, our industry is facing some challenges. This isn't a problem unique to New Zealand, not to pick on my other home country, but there has been some recent examples from the West Island. In December 2018, tenants were evacuated from a 34-storey tower in Sydney. The builder has since lodged legal proceedings against the engineer. Repair works are being undertaken on the building currently. In 2019, apartment owners in 9 buildings in the Northern Territory were notified of structural issues in their buildings. They were told transfer slabs were found to be under-designed for punching shear and bending. They're being rectified at the owner's costs, estimates per building of circa $1.5 million. The engineer involved has been named, deregistered from the Voluntary National Engineers Register, and fined the maximum available penalty of $6,320. In 2019, this one in Canberra, a 120-unit apartment building was issued with an emergency order to prop concrete slabs after it was identified there was an imminent risk of punching shear failure. And more recently, so another one in Sydney, actually, 2019, another building, 10-year-old Mascot Towers, was evacuated after structural concerns were raised. And this was a week before our conference, this one popped up, 2 22-storey apartment towers in Sydney, issued with orders preventing it from allowing owners and tenants moving in after serious defects were discovered in these buildings. Closer to home, back here in New Zealand, we are facing our own challenges. We are still expected to donate huge amounts of time to the development of standards. There's no model around funding of independent technical persons on standards. No model around standing committees and things like that. Engineering New Zealand tell us that we have a mounting backlog of complex disciplinary cases against engineers. We have a competency system that's currently undergoing review, with Engineering New Zealand acknowledging high-profile failures are undermining public trust and confidence. We still have poor designs being designed, consented, and built. We have frustrated building consent officers and peer reviewers, with building control officers saying they're getting pushback from engineers who struggle with the scrutiny, which is a natural part of a building consent process. We have building owners who are being caught out with non-compliant buildings and are losing significant resources and money. So how does this help when we're thinking about new beginnings? When preparing this speech, I found a quote which really resonated to me, and it was that new beginnings are often disguised as painful endings. And look, there's no doubt that there's some painful points in the things that I've just discussed. I know it's painful when there's another headline on RNZ about another building which has not been designed properly. But I also see change. And I think in the future, we'll look back on where we are now as a pivotal moment or time for our profession. I see some new beginnings on the horizon. And while this won't be short term, when I look to the future, it does give me some hope. Case in point, the conference this year was our most successful to date. 4 years ago, we had 230 odd people attend. 2 years ago in Auckland, 260 odd people. This year's conference, we had over 350 people attend. In the last 10 years, SESOC membership has grown from 1,380 members to just over 3,000. Our emerging structural engineers group has been established and is flourishing with over 785 members at the time of our conference. We're making some progress in terms of diversity. To point out the obvious, SESOC has a female president for the first time in 33 years of its history. 3 out of 7 elected members on our management committee are women. Within our professional circles, we have a woman heading the NZSEE and filling the role of President of Engineering New Zealand, and as of a couple of weeks ago, the chair of the New Zealand Geotechnical Society. Recently, Engineering New Zealand launched their CPENG review process. They've been engaging with us on changes around CPENG. So there's some promising signs that we'll see some change coming in the CPENG space. We also have a very real chance of occupational regulation going ahead this time. The consultation document that MB put forward recently, the most recent consultation document, shows a pretty good awareness of the issues that our profession's facing. And more importantly, it indicates a political willingness to proceed with changing the system. We seem to have more of a we seem to have more of a consensus as a profession that we need change, more of a groundswell that something needs to be done, even if we all of us don't quite agree just yet on what that something might be. We've got the construction sector accord, and part of the transformation plan, central government have specifically targeted the regulatory environment for review, and it's quite refreshing to see a government plan acknowledging the inefficiency of having 69 councils processing consents across New Zealand. And starting to actively talk about finding a better way. So a reason for optimism and hope. And it does feel like there's some new beginnings in our future. This year, for what's left of the year and into next year, I'd like to encourage everybody within SESOC to talk about the changes that you would like to see. For me, with everything we do as a profession, from university teachings to MB governments to design office practice, in my opinion, the most important thing is that we have the right systems in place to get it right where the rubber hits the road, that our structures are being properly designed and then built. Call me an optimist, but I honestly believe no one sets out to do a poor job. No engineer wants to design a non-compliant building. The personal toll to all of us, if we're involved in anything around poor design, is huge. Toll on mental health, financial risk, reputational damage. In 2013, John Hare penned a paper on the state of seismic engineering in New Zealand. And in this, he reflected that there's clearly engineers actively in practice who are perhaps not aware of their own limitations. He referred to a paper which talked about a cognitive deficiency as opposed to an ethical deficiency. So to paraphrase, poor engineering is being done by people who just don't know better. And this may be the biggest failure of our current system. University teaches us the principles, but it's when we start working that we learn the application of structural engineering. And in this regard, it can be the luck of the draw. A graduate coming out of university, someone moving here from overseas, these people will be trained by the people they work for. So the people they work for need to be competent. We owe a duty of care to the next generation of engineers to ensure they're being trained by people with the appropriate skill level. That being the case, while I'm SESOC's president, I'd like to focus on service for our practitioner members. By necessity, a lot of the work that we do in the SESOC Management Committee is political, high-level political work. And while that is important, the main thing I want to know as a practicing engineer is how to design it right. And And this needs all of us. We need the academics. We need the academics to keep sharing their research to help guide us in the work we're doing. We need engineers within government to provide technical input to decision making and enable us engineers to have a voice. We need expert practitioners to help get the information out there for our members to be able to confidently do their jobs. But not just that, we need to foster an environment where we are all able to learn from each other, where we're able to ask questions without the fear of being shamed for not knowing the answers. So I, for one, am looking forward to some new beginnings in our future. I want to thank everybody for taking the time to dial in today. I know everybody's very busy and the run up to Christmas is usually pretty crazy, but thanks for joining us. And I hope we hear some more from our members over the next few months about some of the changes coming in our future. Thanks, Laura.
Thanks, Michelle. I think that was really awesome to hear what is on the industry's mind and the priorities, I guess, going forward. So thank you. Next, we will hear from John Hare. John is a structural engineer and chief executive of Holmes Group Limited. He has worked in New Zealand, the United Kingdom, the United States, and is now based in Christchurch. John has extensive experience in both the design of new structures and in the assessment and strengthening of existing buildings. He had significant advisory roles following both the Canterbury and Kaikoura earthquakes. His keynote address at the conference looked at our use of engineering models.
Right. Thank you, Laura. And hello, everybody. I'm just checking that I'm actually on the right. Here we go. So, in the usual way, I like to start a presentation with someone else's wise words, just to make sure it makes up for lack of my own, perhaps. But anyway, setting the theme for the day is this statement here. So, all models are wrong, but some are useful. And I think I should give some background to this talk, which is it really comes, I think, from perhaps, let's say, frustration or inspiration, depending on which way you look at it over the years, of looking at things that have gone wrong with projects in the past and thinking about how we could do better, which is a necessary part of learning. So echoing some of what Michelle has said earlier, we need to work out how to do better. Sorry, just here we go. Looking at this, a lot of this, of course, flows from our use of computers. And I am just old enough, regretfully, to be able to say that I arrived in the office of Holmes, Wood, Poole and Johnson, as it was at the time, many, many years ago, around about the same time as the first computer. Here it is in all its glory. This was the original IBM PC-AT. Gloried in 64 kilobytes of RAM and 2 megabytes of hard drive. So you had to think very carefully when you were doing things, what it was that you actually wanted to achieve with that. Not like today when we've got lots and lots of power at our fingertips, including, for example, the average cell phone, which has got much more computing capability than this does. What is a model? I think is a key question here. So lots of people, some people, at least as children of about my age, probably used to play with Meccano, for example. And as you could see, we could work in those days from a little drawing like this, perhaps, and eventually produce a model like that, perhaps, or better still, work from our own imaginations and come up with something. Times have moved on. We're much more likely these days for kids to have things like Lego to play with. And that's another way of thinking about what some of the original engineering models are, perhaps, that we think about as we grow and develop as people. I could say we then go on to school and university and have some of the creativity knocked out of us until such time as we get out into practice and try and develop it all over again. Thinking of that more in the context of what we do in an actual engineering design studio, I guess the first models that develop are those that we think about. How are we going to solve this problem that we're approaching, this challenge that someone might have set us? And so looking at an example, thinking about how some panels might be erected, you start to think about very quickly about not just what you're doing, but also how it might get done. That may then flow through into the computer I referred to a minute ago, or hopefully a more updated version of that, where you can start to develop the models into something which actually allows us to design that thing that we were dreaming about. And finally, hopefully it gets built looking very much like that original concept that you'll see over there on the left. And so you see through that process, there's many different versions of what a model is which are in play. And it's quite important that we actually think about those, each of them for their individual purpose, and how we use them and how we get the right results from the outcome. Now, a group of two people, David Elms and Colin Brown. David Elms, a former professor at the University of Canterbury, got together at some point and put a lot of names to the different types of models. I think they had around about 16. I'm only interested in 4 that I think are the ones that we mostly use. First of those is that conceptual model, the paper napkin sketch that we do, the thing where we start thinking about how we develop whatever it is that we're setting out to design. That might flow through into what they termed a learning model. And that's where we might start to get onto that computer we talk about and start testing different aspects of that. We might start designing parts and components, so we might have a model which is all of the system that we're looking at. We can then think also of an analytical model, and it's quite important to distinguish between the definition of an analytical model here, which is what we use to validate our solution. So it might be something like a time history analysis, for example, and the learning models, because most of what we think of as analysis is in fact the preparing the assembly of those learning models. And finally, the blueprint models. That's actually what people build from. So that's the drawings, the BIM models, whatever it may be, specifications, effectively the set of instructions that we pass on to a builder to then implement our designs. One of the things we should always avoid is what's termed a prediction model. And in fact, the word predict is a bit of a dirty word, I think, in structural engineering. And the reason is because a real prediction is a forecast of exactly what will happen. And it requires us to know all sorts of things about all of the data which may apply and everything that may happen to our building, assuming we're talking about a building in use. And so by definition, because the building is not even built when we're thinking about it, we don't have the information to be able to predict accurately things that are going to happen. And just to show an example, which I'm happy to say is not actually from structural engineering. It's always nice to learn from others' mistakes, but something which is illustrative of exactly what can go wrong. This is a toll road near Brisbane Airport, which opened some years ago now, nearly 10 years ago, and failed within 1 year of operation. The reason being that the traffic only ever reached 25% of the forecast levels. And it all ended in lawsuits. It was estimated, or I think it's believed, that the engineer responsible for the traffic data may have ended up with about $80 million settlement against them, which is horrendous. But the reason that it went that way was because they actually used their models, which were really only learning models and essentially flawed in a whole host of ways, to make a prediction. And they characterized it as such, and as a consequence, that was part of the reason why they lost the lawsuit, I think. So the important things that we can take from thinking about our models are, first of all, we should never be blindly led by the computing models. That very first conceptual model we develop is probably the most important one of all, because that's where we develop our picture of what success will look like. If those learning models show us something different, we shouldn't assume that they are correct. So we use those models to test our understanding and use them to inform the decisions we make going forward. But what happens if they don't agree? Generally speaking, our computer model should corroborate our conceptual model. And if they don't agree, either the computer model is inaccurate or our conceptual model is inaccurate. But don't just assume that the computer is always right. I find it helps when we're looking at these learning models to think of some key principles. And these have got slightly long-winded titles, but I'll go through them anyway. You don't have to think of them this deliberately, but you want to keep these concepts in mind. First of all, principle of requisite detail. There's a minimum level of detail necessary to actually make sure the model emulates what it is we're trying to model, which is fairly obvious. At the other end of the scale, principle of design and variance. It's sufficiently detailed if the more you add to it, it doesn't make any difference to the outcome. And I think that's one of the traps which is most easy to fall into. We keep on modeling things even though they make no difference to the outcome, fooling ourselves perhaps that we've done a better job in the process. We haven't. We've already confused accuracy and precision, and I'll come to that later. Finally, the one I like best, the principle of consistent crudeness. So there's no point in being more detailed on your model than the crudest part of the system. Another way of looking at that is that you should put the greatest effort into the part of the model that has the most impact in the outcome. Otherwise, you're not necessarily getting at what it is that you need to get to. And I guess another way of looking at that is don't ignore the elephant in the room. Always work where you're going to have the most impact. And so in other words, your model should be as simple as possible to tell you what you need to know, but not so complex as to lose sight of the real issues. And of course, don't ignore the elephants. In other words, make sure as you go through your modeling process that you don't leave behind you something which is going to prove to be a problem later. It's important to consider the roles of assumption and approximation in our models. And the underlying issue being it's never practically possible to model everything. And so we use assumptions and approximations in order to be able to move forward. Assumptions we have to make are generally have to be either conservative enough that we don't need to go back and look at it later, or near enough to what we believe will be the case and we can verify it later. And examples of those, first of all, on the conservative side, think of what we do when we're dealing with reinforcing steel. We assume a 5%, 95% characteristic yield stress. So in other words, the value which is low enough that most steel will be better than that, and we're sufficiently close that we don't need to go back and check every piece of steel later. So we can build that in, and we tend to think of the steel as being exactly that strong, but in point of fact, most of it's going to be a lot better, 95% of it, in fact. On the other hand, an example of something which is sufficiently close is that, for example, when we're doing a preliminary design, we rarely have all of the geotechnical information that we need. So we may do a limited study or even just a desktop study to have some informed values that we can assume for the soil properties. And we know that we can go back later and verify that those were near enough, or we can change the design if we need to. But it's critical that we understand the difference between when we can rest on an assumption and when we need to come back and verify it later. If we think about approximations, we use those to limit the level of detail required or to convey accurately the level of accuracy of what it is that we're doing. It's important, however, that we note that level of approximation, that it should be consistent with the level of information we're wishing to impart. And so an example of the way that we use that in our models, let's say level of detail on drawings. We might assume a level LOD 300 on some drawings. That means we don't need to show every purlin cleat, but everyone knows that they're required. Equally, if we're presenting sketches of information, it's quite often quite a good thing to actually present that in some rather hazy pencil lines on a plan, because then no one gets the impression that your sketch is more accurate than what it really is. So both assumptions and approximations may need testing by running a range of inputs, which we call sensitivity study. And when we're thinking about that, once again, remember that principle of consistent crudeness. Spend your effort where you're going to get the most benefit from it. I alluded earlier to the question of precision and accuracy. And I think a lot of the times those two things get confused, and it's not always clear to people why it matters. So I'll try and show you that, perhaps what the difference is, and come back to that why it matters in a minute. First of all, as these diagrams indicate, it's possible to be accurate and precise, but equally precise but not accurate. When you can see on the top left here how it is, think of darts in a dartboard, we can be consistently missing by the same amount. And it's important to think of that analogy when you're looking at your analysis. Why it matters? Well, first of all, as I alluded to a minute ago, false precision is a common trap. It fools people into thinking that they're right, when perhaps all they are is consistently wrong. it's always important to be accurate, but it's not always critical that we are super precise. And I'm sure many of us have thought about that when we see answers to questions presented to 3 decimal points when really a factor of 10 would be fine. It's always good to be as precise as you can be, but only as good as the data allows it. You can't be more precise than the data. So in other words, if data is supplied to you accurate to 1 decimal point, you can't get a 3 decimal point answer from it. Another important point, as you increase precision, it's harder to be accurate. Now that sounds a bit counterintuitive, but let me show you an example, again, using my dartboard. Is it possible to be too precise to get in the way of accuracy? Well, if you think about hitting or putting a splatter on a dartboard where you are attempting to be quite precise, you can miss quite happily. However, if you attempt to be less precise, then you can take in the whole thing. And so it's possible that you can actually benefit from being less precise. Is too much precision even possible, and certainly is it necessary? Well, I think my line seems to have slipped, but the intention of that was there should be a line through. Is that possible? Maybe come back. Looking here at a chart that many of you will be familiar with, this is the Z factor in 1170. And it's got some pretty refined numbers on it. And it can come down to a matter of being, a millimetre or either side of a line on a map can make a difference in the way that you calculate your seismic loading. But really, when you think about the way, or how accurate, or how precise, I should say, that the seismological investigation is it really that important? And you could argue, and I probably have, that maybe we just need to have a couple of zones in the country. We can still be just as accurate with our designs. We simply won't be so precise in the way that we calculated the loads. And in fact, that might allow us to think more carefully about what it is that we're designing instead of being focused on whether we can shift the isoseismal line a millimetre or 2. Another example of cases where this can be a problem is if we think about, which we've seen, I'm sure many of you have seen, at least in the past, if we start looking at the difference between ISAs and DSAs, which one is better? Now, the example I'm showing you in front of me at the moment is one where a DSA turned up for a small building. This is very shortly after the earthquakes, with 9% on it, which, when you look at that little structure, a single-story school building, you'd have to say, why would that be? And the answer was because someone had looked at it and said, this is potentially liquefiable ground, we'll halve the number. Okay, that would have got it to 18%. Why was it only 18%? And in fact, an ISA, which was formed on a very qualitative investigation, came up to 55%, which is much more representative of that building. Is it more important that we go to precise numbers when we're calculating these things, or is it better to go and have a proper look at what we've got and actually think about the qualitative aspects of this, which might have a greater influence on the outcome? One of the frequent questions which comes up, I think, in people's minds is when to stop modelling. And at this point, I'd simply go back to those principles once again: decision invariance, when you've got the answers you need and when you're not making any difference to the outcome. But I've added one point here, which is when your boundary assumptions align. One of those things we've always got to be conscious of is that we need to make sure that what we're designing is consistent with what we are actually, what we're going to be dealing with. So a classic example of that is when we don't have the geotechnical conditions actually physically on site that we have assumed in our model. And just noting a point here, theories can be right or wrong, but models can be right, but they can also be irrelevant. It's important to bear that in mind when we start looking at those other effects, the boundary assumptions. Another issue I've come across in the past is this question about whether the model drives the design or does the design drive the model. Now, it should be the reverse, but an example of where that can go astray is often in some of the most simple structures we do. If we think of a building such as this schematic I've drawn here, classically we think of our single degree of freedom oscillator, and then we come up with a model that suits that after we've analysed it, which says in order to get that action, we have to pin this thing very hard to the ground, and so we end up putting a lot of piles. It makes for a very stiff structure. We have high seismic demands. If we thought of that a little differently, though, what if we thought about actually allowing some movement at the base? Not so easy to model, but much more reflective of how many structures actually perform, which would allow us to use a simple shallow foundation. The consequence of that is we might have a rocking foundation. Shallow foundations, higher drifts, actually gives us lower seismic demands, provided we can deal with those drifts. And we might end up with a much more efficient structure. The reason why a lot of buildings end up with piles under them is simply because that's the way people think of the models, and that's how we satisfy what the model is telling us. If we ask the model a different question, might it give a different answer? Which leads to one of the worst things I think that can happen, which is part of the issue with models. Sometimes we do stuff because we can. We don't always think about whether the tool, the model, the computer in this case, is leading us forward or whether we are using it. And so we've got to be very careful that although we have the capability to perform all sorts of advanced computer analysis, we might just be kidding ourselves, and we might be going down a path which simply says more precision, but potentially less accuracy. So getting towards the end here, a bit of a summary. What are the key points of success? Well, first of all, know what success looks like. And I think that's where we need to think about what our role is. We need to make sure that we understand that, not from just our perspective of whether we successfully modeled something, but whether that's actually contributing to a successful outcome for our clients. You should always have a clear concept in mind before you start getting into the computer modeling. And you should always really understand what the question is before you start looking for the answer. So you need to be clear what you want from your model and drive it that direction, as opposed to having it lead you. Always use the simplest form of model that can capture the problem. That way, you're not going to get lost in the data that emerges from it, and you're always going to be most focused on what it is you need to find out. And a final one, slightly new. Remember, someone's got to build these things that we design. So only model what can physically be done. And just the slightly tongue-in-cheek version of that, I guess. We might laugh at this, but I swear sometimes I have seen drawings which were somewhat like this. So the final word to everyone there is always be conscious of looking at what your work, looking critically at your work, and being sure that the set of instructions you're issuing, those blueprints, are actually something that can be executed. Thank you very much.
Thank you, John. There are some great messages to keep in mind the next time we're tasked with an analysis project, I think, before getting too caught up in the detail. For those who haven't been to a conference before, there are a range of different styles of presentations, from the longer keynote addresses given to the whole conference to the paper presentations, which are typically 15 minutes. One of the more fast-paced sessions are the lightning talks. Each presenter has just 5 minutes to capture the audience's attention and deliver their message. So we have two of the lightning talk presenters next. First up is Andrew Blackford. Andrew is a structural engineer as part of the pre-construction team for Naylor Love. His lightning talk at the conference looked at the design to construction process, a seismic chasm or a bridgeable gap.
Brilliant. Thank you for that intro, Laura. Afternoon all, and thanks for dialing in. So yeah, design to construction. All of us have been through this evolution of turning our thoughts, drawings and specifications into the built environment. For some, and on occasion, it may not have been a successful journey. Rightly or wrongly, success these days is often defined by price, and in particular, whether the price to build matches the budget allowed for. In my experience, it is rare that an unsuccessful outcome is due to the structural environment being too efficient or too heavy. Materials are easily quantifiable, and provided they are on the drawings, will be accounted for in the project budget well before a contractor provides their price to build it. More commonly, it is what is not shown or the unknown that leads to a poor outcome, and therefore this talk is a request that you tell the story behind your designs and how you see them moving from the theoretical to reality, from design to construction. No one will understand your design better than you, and if you aren't telling the story, it's quite likely it's not being understood. In a traditional project delivery model, this conversation is with the rest of your design team, and in particular, your QS. In an ECI or DMB model, then it is with your contractor. Describe how you see the structure going together, whether the building will stand up on its own or require temporary support. Does it meet the 6-month design life criteria while it is being built, or will it require supplementary bracing? Don't be adverse to adding a few notes to your drawings to convey these messages. It is often the most cost-effective way to portray and understand what is required. Remember critically that you are designing the final state, whereas the contractor is more concerned with the journey to that final position. If there is a misalignment between the design assumptions and the contractor's methodology, you are likely to end up in a contractual debate. As an example, is the restricted access under this floor until the props are removed an issue in terms of progressing fit out and services installations on site? Or does it not matter as the space is lightly serviced? Was it even considered during concept design that what goes in the building might be more important than the building itself in terms of meeting the target deadline and the client's brief? You know, a good structural concept, and I think this is one key message that we often sort of fail to recognize as structural design is that a good concept is one that is sympathetic to the remaining 75% of the building that needs to be built. You know, as structural engineers, and you know, roughly speaking, that's what we are responsible for in terms of cost. How do these services fit into the space provided once the structure is installed? You know, here's an example here of a pretty congested hallway in a hotel area. And will, in order to fit all this building services into this space, require fully coordinated 3D modeling to ensure that it does? You know, were alternative schemes discussed that provide more flexibility? And if so, why weren't they presented as alternatives at the time of concept? Generally, there will be a good reason as to why you ended up with the concept you did. And so it's often that these intangible elements that can't be measured in kgs of steel or cubic meters of concrete that lead to a misalignment in expectation, a gap between what we perceived and what actually eventuated. The gap is not due to a lack of skill or thought, but often a lack of communication. Often you will know exactly how you perceived the building going together and what will be required. It's just that nobody else did. So are terms like programming, procurement, construction sequencing, tolerance, temporary works front of mind when designing a new structure? Probably not. They are historically the domain of a contractor, but increasingly they are having a significant impact on the cost of construction, and therefore they should be being discussed during the design phase of a project. If you don't understand these terms, then who else in the design team does? Who is providing the advice and where is the knowledge coming from so informed decisions can be made regarding buildability, build durations, and how these affect pricing? Contractors know this stuff, and without exception, they will share it with you. You just need to ask. So should we be strengthening the links between engineers and contractors so the relationships are there to foster collaboration and information sharing so that designers can learn and designs are cognizant of these critical aspects of construction? In my opinion, the answer is yes. So how could we go about this? At the individual level, one of the most beneficial things you could and should do to develop your career is build wide contact circles within the construction industry, whether this be with main contractors, subcontractors, or other consultants. Their views will be different to yours, and regularly seeking their input will enable you to develop a more holistic view of design. Talk to them regularly and ask for feedback on present and historic designs. Don't be afraid to discuss your current projects with your peers and other contractors, even if the project hasn't come to market yet. There is really a commercial reason to prevent you from seeking advice. At the company level, Question whether your designers have enough site time and the opportunity to build relationships and contacts with the wider industry. Consider reciprocal secondments with some of the larger main contractors. Many of them now have structural engineers on their payroll, and most would be keen to give their site engineers the opportunity to develop better design skills. And at the industry level, do we provide the right training for engineers, and are there enough opportunities for contractors to present their views on designing and design practice? In my opinion, with better collaboration and communication and training, we can bridge this gap. Thank you.
Thanks, Andrew. A good reminder about things we need to think about during design to ultimately have a successful building. Next, we have Annie Scott. Annie is a structural engineer working for Jensen McCarley and Associates in Auckland and was a recipient of the SESOC ESE scholarship to attend the conference. She has 7 years of experience across New Zealand and the Netherlands and is passionate about sustainable structural engineering and working for clients with a passion to drive this change. Her lightning talk is on understanding the value of a talented drafter.
Cool, perfect. Thanks, Laura. If we could just flick over one slide, Andrew. Perfect, thank you. Kia ora, everyone. So my name's Annie Scott. I'm a structural engineer born and bred in Auckland, and yeah, working at Jensen McCarley and Associates. Today I'm going to talk about what I believe the role of a talented drafter can be. So ensuring clear and concise communication is one of the most important aspects of structural engineering. I'm talking both communication internally and externally during both the design phase and during construction. At the end of the day, our structural engineering design is predominantly communicated through drawings to build off. So many spreadsheets, analysis models, hand calculations, all go into producing these drawings. But if the drawings aren't clear, if they don't convey the story, or if they just don't look good, then what's the point? Now, don't get me wrong, understanding key engineering principles, completing adequate calculations, and following a good review process is imperative to getting these drawings right. The buck stops with the engineer and the PS1 signatory, and you can't get correct structural drawings without quality structural engineering. But you also can't get quality drawings without a good drafter. And I believe a huge part of completing a project successfully is to have a knowledgeable drafter as part of the process. I was lucky enough to be paired with some senior, really talented drafters in my first few years of work. They questioned my details, helped me visualize my designs, and pushed back when they knew there was a better way to do something or a more efficient design. And it's this collaborative two-way approach to engineering that I love and something that I really think needs to be encouraged. I want to iterate on this point, how valuable pairing a younger engineer with a senior drafter can be. Drafters can and should be part of the mentoring process. I've talked to other peers prior to this presentation and they all agree. I once spent far too long trying to work out the geometry of some really tricky stairs. But after sitting down with a drafter for half a day, they helped lead the design process, working out the stair geometry, where the landings should sit, liaising with the architect, leaving me to focus on the structural engineering. Another example is designing reinforced concrete moment frames. You get to the beam column joints and nothing fits. But this is a process where a drafter can make a really huge difference by sitting down early on in the process to draw the beam column joints and work out the geometry. As a young engineering graduate, let's be frank, you don't really know a hell of a lot. So much learning is done on the job in those first few years. And for me, a huge part of that learning was about the practical side of engineering. John sort of touched on how we're becoming so advanced with our modeling that we could actually design structures that can't be built. And I think this is an area where a structural drafter can really help ensure that our designs are buildable. And buildable in a way that is both cost efficient while maintaining some degree of practicability. I've also recently experienced how time valuable a good drafter is. When you don't have to spend time marking up clashes, terminology inconsistencies, or errors in the drawings, you can spend more time focusing on the engineering. And I mean, engineering is already time consuming and hard enough. In recent conferences, this year, we've talked a lot about industry collaboration. We've heard from insurance brokers, mayors, property owners, developers. So let's get drafters as part of this involvement too. As BIM and technology continues to advance, our clients, contractors, they only expect more detail and more coordination from our drawings. Drafters are being relied upon so much more as part of this process, especially on big complex jobs, where a significant part of the challenge is working out the geometry and coordinating with the wider design team. And as we expect more from our drafters, having a good working relationship, good training programs, and including drafters in technical development is so important. The learnings need to continue to be a two-way street. Looking back on the jobs I've been a part of, the ones that have been the smoothest and the most successful are definitely the ones where I've had a talented drafter by my side. As the industry moves towards diversity of thought, let's make drafters part of this process too. Thank you.
Thanks, Annie. A nice perspective on the drafting process there. Finally, we have Hamish Tocker. Hamish is a structural engineer at Holmes Consulting based in Auckland and was another of the recipients of the SESOC ESE scholarship. Hamish and his co-author Matt Cutfield have worked on a number of assessment and strengthening projects for historic buildings, including projects based in the Netherlands. Hamish and Matt's paper looks at some options for dealing with earthquake-prone masonry buildings, with an emphasis on buildings located in regional centres.
Ngā mihi kia koutou, I'm Hamish, and I'd like to take a road trip with you. So I want you just to imagine that we're going on a trip on this sunny afternoon, and maybe we're getting a bit hungry and we're going to pull into a small town somewhere. You know, the small town that has those really good sausage rolls? And I want you to imagine the street that we're about to pull into. I'm sure that in your head you saw something that looks a little bit like this. As structural engineers, we probably recognize that these are unreinforced brick masonry buildings and that they're likely to be earthquake-prone buildings to go with that. But when you zoom out of the community and start looking at it from the air, you start to see the scale of some of the problems with those earthquake-prone buildings. So each of those orange dots is a marker from the earthquake-prone building register showing which of the buildings have been deemed to be earthquake-prone. And it's not just Fielding as a community, it's also other places all around New Zealand. I'm just going to show a fairly random scattering from Levin to Gisborne, smaller towns near Whanganui like Martin, Waipukaro, Waimati in the South Island, or nearer to me in Huntly. So those masonry buildings really are clustered in the shopping streets of the small towns of this country. So the way that we deal with those buildings at the moment is through the Earthquake-Prone Building Act. And what we need to do is to assess each of those buildings individually to understand exactly how earthquake-prone it is. So many of you will be very familiar with this process, which takes us from an ISA to a specific detailed seismic assessment, a number of design phases, and then potentially some consenting before we start spending money and doing work that is improving those buildings and the way they might perform in an earthquake. And it is a multi-phase process and can be quite a costly process. So skimming over this just for time, but there has been quite a bit of research into the effects that the Earthquake-Prone Building Act has on those communities. And to summarize, it seems likely that demolition of a large number of those buildings or abandonment of some of those buildings is predicted, and that the status of them, whether they are heritage buildings or not, may not have an impact on which ones are retained. The most recent data is from MB, who published earlier this year a survey they'd carried out in 2020, showing that a number of the territorial local authorities are not that confident that they will get to the remediation by the deadlines in the Earthquake-Prone Building Act. So if we look at what the outcomes we might predict from the current settings, we've noted that some of those buildings are not going to get retrofitted by the Earthquake-Prone Building deadlines, or perhaps at all, that they're likely to be clustered into regional centres, and the rental returns for those buildings are relatively low, which affects the ability of the owners to fund a bespoke strengthening program for those buildings. Similarly, if it's difficult to fund that strengthening, it's going to be difficult to replace those buildings. The consequence there likely to be loss of not just assets that belong to the owners, but also some of the cultural amenity and perhaps the historic heritage that those buildings embody and that they deliver to the communities which they are situated in. And of course, if owners are trapped in a situation where it's difficult for them to respond to the Earthquake-Prone Building Act imposition or stimulus, they're also not able to make safety improvements to those buildings for an earthquake that we might get later this afternoon or tomorrow. So let's look at what the options might be. the Earthquake-Prone Building Act we've shown imposes some costs. So one option is that we leave things more or less as we are. And so we expect that some demolition or abandonment of those buildings is a likely consequence. So an alternative option might be for the government to increase funding, which goes towards strengthening of those buildings. It's possible that there's a somewhat limited appetite for public money to fund the strengthening of private assets. And that's demonstrated relatively recently by the Heritage Equip Fund, which the government was running, not having been funded in the most recent budget. So an alternative option, which I'm really here to discuss, is what can we do with the engineering? And is there a way we can lower the burden of engineering for those structures in order to make strengthening a simpler process? So the opportunity that exists to let us consider doing that is that the unreinforced masonry buildings in New Zealand were built within a reasonably tight time frame between about 1880 and about 1930. Many of them are constructed very similarly, and the set of details which they were used for construction and the methodologies by which they were constructed is a relatively constrained set, and it's relatively well understood. There's been quite a bit of testing from academics and others that have established what the failure modes of those masonry structures are likely to be, and it's backed up by international testing and studies as well. And in fact, some standard retrofit details to deal with those major failure modes do exist and have been published by MB. So an option is that we could allow a non-specific design of retrofits, which can be applied without a specific engineering assessment to some of the buildings meeting those criteria. So we talk about that as simple strengthening in our paper. And I figure if it's really simple strengthening, it should be able to fit on a slide. So I'm going to try and do it in one slide. So if we do a simple strengthening non-specific design scheme for a unreinforced masonry building, we would always be restraining or removing chimneys or precarious parapets. We might look at canopies if the building has a canopy and its connections need to be considered. And we would always look at the roof to wall and floor to wall connections, which those of you who've worked on masonry buildings will understand are always a key part of those strengthening programs. And similarly, we would look at doing that at a pretty conservative set of centers rather than looking to calculate the demand for each individual building. So for some buildings, out-of-plane walls may require to be strengthened with strongbacks, potentially timber strongbacks in many cases. And some buildings will require their diaphragms to be strengthened, noting that when we're dealing with a series of shops or a row of buildings, it is possible to think about those diaphragms acting in a kind of collective way, especially if we're able to strengthen the connections. So the intention here is to provide something which is somewhat analogous to the 3604 or 4229 non-specific design standards which already exist for other materials. And to support that idea, we've been developing some lookup tables, which will be published in some future work, which is sort of in progress. Really, the idea is to direct people towards the MB details with some additional details added where required. So what set of buildings does this proposal apply to? Jason Ingham and Alistair Russell did some work 10 or so years ago, dividing URM buildings into 7 different typologies. And we're really looking at typologies A to D, which is 1- and 2-story isolated and row buildings. We also think it might be useful to consider whether a good policy option is to constrain the buildings which are eligible for the scheme by value criteria. So it could be possible to use a measure rather like CV to constrain this scheme from being used in very prominent buildings in large cities where those retrofits can perhaps be funded by other methods. It's also useful to, I think, or necessary to limit the geometry of buildings for which this might be relevant. There would only be certain story heights and shapes and only certain Z factors for which this kind of scheme could be applied. So let's look at cost. When the Earthquake Prone Building Act was promulgated, there were some quite wide estimates of the cost that would be incurred by owners in carrying out what the Earthquake Prone Building Act required them to do. And so those estimates are also aging a little bit since the last recent one of, before the Act was promulgated in 2017. So there is also some research, and this partly comes from the United States, where some West Coast cities have instituted a similar scheme, which suggests that the cost reduction could be in the region of 30 to 70. Fair enough, that's quite a wide range, and it does depend on the way that the scheme is implemented. But the research indicates that there is significant cost saving to be had, which may make it possible for owners to actually carry out these schemes as opposed to just having to demolish or abandon their buildings. So one thing that the keen-eyed will have noticed is that we have deliberately excluded in-plane strengthening from any of our commentary around this scheme. And the reason for that is partly that when you look at those in-plane penetrated walls you're seeing in the picture there with a simple strength-based or force-based analysis, it may not be capturing the full capacity. They may appear to be more fragile than they really are. And it can be that nonlinear or pushover or time history analyses can reveal some innate capacity which is there. So really what we're saying is we don't think that the failure mode is quite as critical as it may appear. It's also possible that the buildings have some abilities to support each other once their diaphragms are strengthened, and that could be through a torsional mode or through sort of load sharing between the buildings. There are, of course, a number of issues with that, and we're working to develop some more robust engineering principles to show that some of this is the case. So lastly, looking at percent NBS. Percent NBS is the method that we use for capturing both the likely performance of the buildings and also the risk which they present. And it requires an engineering analysis to be carried out that looks at the building on a component level. So what that requires is a relatively specific understanding of the way the building is likely to respond in the engineer's mind. And engineers need to develop that for each individual structure in order to be able to put their signatures and their names to the score which they're giving the building. There really aren't any shortcuts to define NBS, and we think it's appropriate for many circumstances and for many buildings. However, if we accept the premise of this paper, which is that there is a large group of buildings which just won't receive a specific analysis or strengthening program, and that's largely for financial reasons. If we decide that the do nothing option, which might lead to demolition or to abandonment, or the increased public funding options are not preferred, it might be possible for us to accept that we can do a non-specific simple strengthening scheme, which we know will make the buildings and the people in them safer, without seeking to quantify exactly how much safer through giving the building a specific NBS score. And I was reflecting on what John was saying earlier in terms of accuracy and precision and thinking about that. And so if we were able to come up with such a scheme, that might remove a number of the steps in the process. We may no longer need a detailed seismic assessment. The design phase could be covered by standard details, and it's possible those details could even be covered by some consenting. So we may be able to move straight from identifying the building as potentially earthquake prone to carrying out work which improves the building and its performance. So there are a number of potential issues which I won't look into in great detail for time, but there is some commentary on those in the paper that accompanied our talk, which you can get through the SESOC website. To summarize, the research shows that there are a large group of a cohort of buildings in smaller towns which may not be strengthened by the Earthquake Prone Building Act deadlines. In order to avoid demolition and abandonment, we might look to permit some standard detail strengthening to be carried out to a subset of those buildings. And it may be that percent NBS is not the only effective way to decrease public risk and to identify that we've made the buildings stronger and safer. Thanks for your time.
Thanks, Hamish. Those are some great ideas that really make us think about how we approach some problems. Good afternoon, I'm Amber Coulthard, a member of the SESOC ESC committee, and I'm based in Christchurch. Thank you all for attending today, and especially thanks to our presenters who have taken the time to represent their papers that they did at the conference. It's been a really good taste of the highlights of the SESOC conference, and it's been really good to be able to share that with our emerging crowd. The SESOC has an emerging structural engineers stream, and thanks to the SESOC ESC scholarship last year, the ESC presenters, including Annie, Hamish, and myself, and a few others, were able to present at the conference. The other ESC topics were ranged, including some important aspects of being an engineer, what happens when we make mistakes by Vinnie Montalto, the importance of taking care of our mental health by Michael Geddes, a presentation on sustainability by Phoebe Moses, and temporary works for the new Brighton Pier by Ben Exton, and my own presentation on the Ashburton Library and Civic Centre. The next conference will be in 2023, which is not next year, but the year after. But you can start thinking about what you might want to share with the industry, as the call for abstracts will happen late next year. In the meantime, when we're able to meet in person, the ESC are wanting to put on more regional lightning talks. The idea is that we'd have 5 presenters, each giving about a 10-minute talk, similar to what Annie and Andrew did today. Basically giving an update on what they're up to, anything interesting. It might be an overview of a project or focusing on a complex design detail or some lessons learned. We wouldn't want it to be too formal, just presenting to the emerging structural engineers crowd. If you're interested, let us know. And as a final plug, we're always looking for new ESE committee members. I know our members in Auckland and Wellington are looking for some help. So again, get in touch. Thank you everyone for joining today and have a good afternoon.